All right, good evening, everyone. This is Astro 10, Evergreen Valley College, and we are focusing today on, in fact, this week on chapter 4 of our book that has to do with interactions of Earth and Moon. And we are also going to take a look on Moon's phase, how to be able to look at Moon in the sky and identify its phase and predict uh, time of rising, time of setting, using the knowledge that you can derive in this chapter. So, first of all, Earth is round. That's a picture of Earth taken from space, believe it or not, from a car. And we go over the concept of latitude and longitude and coordinate system in astronomy. So, in astronomy, we
You
have.
lost your mic.
I'm sorry, say it again.
You lost your mic, I think. All of a sudden, your audio went way down.
Oh, is that right?
Yeah.
Let's see.
You moved something. I don't know what, but you moved something.
Can you hear me? Can you hear me now?
Yeah, I can hear you now, but let's see how it goes.
Wait a second.
I think maybe you need to move the laptop closer to you, also.
Yeah, maybe. I raise up the sound and I'm trying to be closer as I can.
Okay.
Okay, so
you have to eat the microphone.
Yeah, let's try again. Let's share the screen. All right, and move this out of the way. So Earth has a system of coordinates, and then you can locate any part on Earth by its latitude and longitude. Latitude is defined as a circle above the equator with certain degrees with respect to Earth center. And longitude is also a certain amount of degrees with respect to one of these major circles that pass through Greenwich. And you can define longitude east and west. And Rick, you help me here. What is the longitude of San Jose? Is negative is 120
37 degrees.
That's the altitude or latitude.
Yes. And yeah, latitude is 37 degrees, and the longitude is
121 west.
West.
Yes. So that's locates San Jose basically in the system of coordinate, latitude and longitude. But we can think of a similar system when we apply that to the celestial sphere. So celestial sphere, again, as we saw previously, is not a real sphere, but it's very useful when you try to locate objects in the sky. And there are two coordinate systems we use a lot, or at least we mention more often in our courses. The first one is the so-called equatorial system. In the equatorial system, the coordinates are given by right ascension and declination. And in the horizon system, the coordinates are given by the so-called altitude and azimuth. So let's see how this play out. Oh, I don't have it here. I think I have a simulation I would like to bring. So altitude azimuth is an angle. If you think in a celestial sphere, and if you think you are resting on a flat surface, and then you look around, and then you can devise clearly your horizon. And horizon is an imaginary line divide this flat surface in the sky. So if you can imagine that, you can divide this horizon in north, south, east, and west. So azimuth is an angle that is counted by the amount of degrees from north, counting as you look down on it, counterclockwise as you look down on it. So from north to east, you have 90 degrees azimuth. So south is 180 degrees azimuth, and west to 70, and then back to the north. So if you have a star like this star over here, right? So you have a star in the sky, so you can track this star by its coordinate, equatorial coordinate, has azimuth and altitude. So the star rises with altitude 0 because it's pretty much flat in the horizon or against the horizon. And then as the star moves across the sky, it rises up and then crosses the meridian due south, and then it starts lowering on your altitude all the way to when again is 0 altitude. But the azimuth keeps changing all the time, right? So let's see the progression of the star. If I can run this simulation, can I run this? Oh, it doesn't show the move of it. But if the star, I have to do manually. So if the star, let's say, rises in the eastern sky, so basically reach maximum height due south, and then start setting in the western sky. So the azimuth angle in blue keep increasing, and the altitude angle starts 0 and then rises up, reach maximum value when it crosses the meridian line, and then falls down when it crosses the equator again. So in our telescope up in the observatory, the telescope we use, it has pretty much altitude and azimuth. The other coordinate system, the equatorial coordinate system, use right ascension and declination, which is the equivalent of latitude and longitude, except we use celestial equator as a reference. So this will appear in the slides. I hope so. So let's take a look at seasons. So why do we have seasons? Oops, what happened? Sorry about that. There you go. So why do we have seasons on Earth? In fact, I saw a book, in fact, was a high school in Brazil that go on to explain Kepler's law, that the orbit of planets around the sun is not a perfect circle in an ellipse. Sometimes the planet is closer to the sun, sometimes the planet is further out, and it goes on to, and of course this is several years ago, right? So don't have a bad picture of my country. You can have a bad picture of my country, but in this particular, I think we made a big progress. And then the little book would go on to explain that, well, the seasons are caused by this elliptical path of Earth around the sun, indicating or suggesting that when Earth was closer to the sun in the so-called perihelion, so Earth is closer to the sun, that would be summertime, and when Earth is further out, would be wintertime, right? That seasons are explained that way. So that is not it. That's really not it. So certainly when Earth is closer to the sun, it might receive a little bit more of sunlight, but that is not enough to drive the seasons, as we know. And because the orbit of Earth around the sun is, although elliptical, is not so eccentric. It's almost a nice circle. So why seasons? This is important. So you are going to see this question on your midterm. So the seasons is caused by this very inclination of Earth axis of rotation. If you can see the hand tool in your display. Can you see the hand tool that I'm moving?
Yes.
Okay. So this axis of rotation, as you can see in the display, is always pointed at the same location in the celestial sphere, and that is Polaris. The north celestial pole, where this axis of rotation, this broken line, happens to be pointing at, is always very much near close to Polaris, about 1 degree off. But you see, in the summer solstice in the northern hemisphere, better saying the northern hemisphere, the northern hemisphere happened to be tilted towards the sun, whereas the southern hemisphere is tilted away from the sun. And then 6 months later, when Earth is in this position, now the northern hemisphere is tilted away from the sun, whereas the southern hemisphere is tilted towards the sun. So summer and winter occur at the same time, northern and southern hemisphere. So seasons like summer or winter is not caused by the proximity of Earth to the sun, but is caused by this tilt of Earth's axis of rotation with respect to the perpendicular, this straight line, this perpendicular to the ecliptic plane, which is the name of Earth's orbital plane around the sun. And these two other positions here, in September 21st and March 21st, it marks the point in which both hemispheres happen to be illuminated the same way. And that's why this name equinox, which is the same thing as equi, the same, nox, light, so it's the same illumination in both hemispheres. So the difference between vernal equinox and autumn or fall equinox is that in the vernal equinox, the Earth is moving towards, in its orbit, is moving towards the summer solstice. In other words, Earth is, the sun apparently crosses the celestial sphere, or Earth is crossing the celestial sphere, and apparently from Earth we see the sun moving north as it crosses the celestial sphere. So in both equinox, vernal and fall equinox, those are the points where the celestial equator and the ecliptic line, they both meet at the same point. And for astronomical reasons, we define the vernal equinox March 21st, the point where the sun exactly crosses that point. So no matter years and years in the future, thousands of years in the future, March 21st will be defined as the point where the sun is crossing the celestial sphere, and we define that day as March 21st. Very important. So from Earth, on March 21st, you look towards the sun, right? And you see the sun against a given constellation. So these constellations might change because of Earth precession. The precession of Earth's axis of rotation wobbles and goes in a cycle of about 26,000 years. And therefore, the constellation in which the sun appears to be in March 21st, which is the beginning of vernal equinox, keep changing slightly over the course of 2,000 years or so. Okay. Let me show this animation here, which again indicates the reasons why summer tends to be hot and winter tends to be cold. So we are in March 21st in one of the equinox, which is the vernal equinox. As you can see, the sun rays in yellow, depicted here in yellow, they reach Earth, north and south hemisphere the same way. The illumination in both hemispheres is basically the same. So as we progress towards summer, now the sun is shining at less angle towards the northern hemisphere, and that quantify and qualifies the so-called summer. And as you go towards winter, we pass the fall equinox, but when we get to winter right now, the sun is shining on the northern hemisphere, as you can see right here, with a very low angle. So what does it mean? Well, it means, as if you look in the southern hemisphere, the sun shining more directly over the surface. It means that more energy of the sun is being concentrated by square inches. Whereas in the winter time, since the sun is shining with an angle, that same energy now is spread over a larger area. So that same energy, instead of being concentrated in a smaller area, like in the summer, and therefore dragging and dumping more energy per square inch, in the winter, because of this angulation, then the energy is spread over a larger area. This is one of the reasons why in the summer we feel hot, and in the winter we feel cold, right? The second reason is, as you can see in this simulation, the amount of hours the sun stays up above the horizon in the summertime is much larger than it is in the winter time. So these two factors, one, the number of hours the sun stays above horizon in the summer, first of all, and second, the inclination of the sun rays on the floor being more directly, more closer to the perpendicular to the floor, concentrating more energy to the floor. So those two factors contributed to make the summer hot months and winter cool months. Where is it? Yeah, you can see in this picture here quite well. So take this area, 1.04 square meter, and then in the winter, the area in which the same energy is radiating or falling is much bigger. In fact, it's almost the double. So that per square inch of the floor, the soil receives less sun radiation. Sun's position in the sky on different months. Take a look at this picture here. This is a dude sitting on its horizon, right? East, west, south, and north. Celestial equator is here defined. And the Earth axis of rotation is here defined as well. So in the summer solstice, the sun's path in the sky has this orientation here. And then when it goes to the equinox, the sun is pretty much appearing to be associated with the celestial equator. In fact, equinox defines the position where the sun is crossing the celestial equator. And then in the winter time, in December 21st, the sun is at a lower latitude. So let's see the same fact in an animation. Oops, not that one. So here's a nice little house and our horizon. So imagine you are looking due east. In our observatory, we are looking towards the hills, right? So we have a bunch of little hills there. That's our good sky. And south is where the parking lot is, and north is where Polaris is. That's the best way I can say it. So if I start playing the animation, that is the apparent path of the sun in the sky every time it's rising. In the winter time, the sun is rising more to the south. In equinox, it's rising exactly due east. And in the solstice, summer, it's rising closer to the north. So the path of the sun in the sky in the summer solstice, it rises closer to the north. It goes up and almost hit our zenith point. It doesn't because we are in San Jose. Latitude 37 is not 23.5, so it's a few degrees below our zenith point. And then it sets down in the western sky closer to north. So the sun stays longer hours during daytime, more hours during daytime. Okay. Now, what is the difference between sidereal and solar day? The book goes on in a major discussion on calendar, which, and the discussion is very good because we went through a major change in the way we think about time. So if you go to ancient cultures, the ancient cultures use the moon as a source to provide information for calendar, and we inherit some of that tradition. Think about month. The root is moon, and the moon goes through phases, as we studied before, over 29.5 days, which is close to 30 days, which we define a month. So when in olden days we would say a see you in a month, it means, or see you in the next moon, which means, well, the moon is full now, and I will see you when the moon is full again, about 30 days or so. So that's the idea. When civilization started to be built in different areas, using the benefits of rivers and floating areas and agricultures and all of that, then the sun became important. And then we start using the sun to keep track of time, which we do today. So if you think about our calendar is a lunisolar calendar, in the sense that we have elements of the moon in it, but it's primarily controlled by the sun. And I just mentioned previously that the beginning of vernal equinox corresponds to the moment when the sun is crossing the celestial equator. It's a very definite astronomical position in the sky. So, what is the difference between sidereal day and solar day? When you see this word sidereal day, sidereal month, sidereal lunar month, so sidereal is a word that is used to establish a correspondence with stars. So sidereal day is how long it takes Earth to complete one turn in respect to the stars in the very far away. So stars that are supposed to be fixed, and as I keep repeating it on and on and on, nothing is fixed in the universe. The stars are moving 30 kilometers per second, 50 kilometers per second, and we can detect this motion if we use proper technology, Doppler effect and spectroscopy, so on, so on, so on. But they are so far away that we do not measure, we do not perceive these motions going on. Now, but Earth goes around the sun every day. Right? So Earth gives one turn in respect to the stars, and during the time it's giving a turn in respect to the stars, it also moves around the sun. So there is a difference between sidereal day, which is the true orbital spin of Earth, or the true sidereal day is the true time that takes Earth to complete one spin around its axis of rotation, and the solar day, which is the time it takes the sun to get out its position and go back to that same spot again the next day. So the difference is significant. We take this the solar day as an average over this spin along the year, and we set that to be 24 hours. Now, the sidereal day is how long it takes Earth to complete one spin around its axis of rotation, and this is slightly less. It's 23 hours and 56 minutes. So let me show in this animation here what do I mean by that. So this is Starry Night. Oh, no, 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 I don't want to do that. The Starry Night with my Macintosh and without mouse is not friendly at all. Okay, let me see what I got here.
Alert from numbers.
Okay, so that's the sun. Oh my goodness. Come on, don't. Okay, just stay there. Hey, Trisha. See you there. Okay, so this is good. Oh no, I'm not doing this motion, I swear. What is going on? Oh boy. I think I know what it is. I have this Wacom tablet. Okay, I'm gonna bring the sun close to meridian. I'm allowing the time to go very slowly. Okay, stop there. Okay, that's good. Let me take a star. See this tiny star over here? Let's see if it has a name. I want a star that is take one day further. Oh, that's the moon there. That was coincidence. Okay, see this star over here? That is a Tycho 5801-877-1 star. So that's a star. This black thing is the moon, is a new moon. And the sun is crossing the meridian 12 hours 21 minutes p.m. February 15. And what I'm gonna do, see I'm gonna advance one day. So I went one day, the sun is back to its meridian line. It's not exactly the same spot. It's complicated, but it's close to meridian. But look what happened with the star. The star went about 57 arc minutes. It's almost 1 degree. See that? It's almost 1 degree in one day. So why is that? So in the day before, the star was close to meridian, and one day later, the star apparently in respect to the sun. If you have the sun and the star on a bet to see which one is faster, the sun would be slower. So the star would be crossing the meridian again the next day before the sun by 1 degree. Okay? So we got that? So let's go back to here. So here's Earth looking at the sun. Next day, day 2, day 1 is here, I'm sorry, and day 2, Earth is down here. You look at the sun, and Earth has progressed 1 degree in the sky, basically. So, which means if you are probing a star in the very far away, right here, that star appears to move in respect to where the sun was 1 degree. In other words, every day, the stars in the sky, in respect to our local time, and sun is the one controlling the local time. So in respect to the sun, in respect to our clock, the stars are moving westward, and that's what Starry Night is showing, right? The star moved westwards, towards west. West is to our right-hand side. The stars are moving westward 1 degree every day. So in 2 days, 2 degrees. In a week, 7 degrees. In a month, 30 degrees. In 2 months, 60 degrees. 3 months, 90 degrees, you don't see the star anymore in the sky. Does that make sense? So because of Earth revolution around the sun, because of this revolution, we see certain constellations during certain months, and then 2 months later or so, that constellation is not in the sky anymore. So we have a tendency to see these constellations drifting westward every day. 1 degree here, another degree tomorrow. Next thing we know, past 1 week, 1 month, our Orion is going to be off view at the time we like to see, which is about 9 or 10 p.m. That's when we have our public viewing. Are we all there? Okay. Stonehenge. I have some slides on Stonehenge and some presentation. Next Monday is a holiday, but if you guys are not doing anything, I will join and do a presentation on Stonehenge, which is pretty cool. And I try to put the slides together. So Stonehenge was there are different sources. If you go to History Channel, the people doing history, they say, "Oh, that's a burial site," and they are right in saying that because there are several burial sites in Stonehenge, but it doesn't mean that Stonehenge was built to be a burial site. My impression is people who had power at certain time in history, they used that site to bury themselves there because they had power. But Stonehenge seems to be an observatory built to observe and to mark solstice and primarily solstice and lunicist, and keep track of moonrise and moonset in a very, very exquisite detail. And there are several different parts of the Stonehenge, especially the old parts, about 2000 before our time, that the moon was one of the main targets in there. They would put sticks in certain locations and keep track of the moon rising and mark the position with detail. But I hope to place it in there. So moon's phase. There are a few things in tides. So those are the 2 things I would like to finalize with. So tides are caused by primarily by the moon, but tides are exerted on Earth by both the moon and sun. And so if you can imagine, in full moon, the moon is here, Earth is here, and the sun is in the other side. So they both, which means moon and sun, they combine to stretch Earth in such a way that you cause the tides. And those tides are called spring tides. Now, when the moon is in a quarter phase, which means you have a 90 degrees angulation, moon, earth, and the sun, uh, although the moon exerts most of the tidal force on Earth, the sun also exerts some, which means the sun is kind of a driving and pulling Earth in a direction that cancels out some of the effect the moon is exerting. So although the moon is controlling the high tides are not as high as it is in spring tides when you have a perfect alignment between moon, earth, and the sun. And I'm talking about the new phase and the full phase. So when the moon is in the new and full phase, the high tides are the highest possible. And when the moon is in the first or last quarter phase, still we experience high tides twice a day, but it's not as big as it is when the moon is full or in the new phase. But let's look at moon's phase basically. So the phases of the moon are caused by the combined effect of the sun, which is the source of light in our solar system, and by the fact that the moon itself orbits Earth. So if you look down on the system, sun, Earth, and the moon from north, what we see is the moon going around Earth in a counterclockwise direction. It goes in a counterclockwise direction like this, and we call this counterclockwise direction the prograde or direct motion, which was the original motion in which the disks, the circumstellar disk around the sun was primarily going, and out of this disk, planets and satellites and asteroids, most of the comets came through, and they inherit that type of motion. Now, in the new phase, as you see over here, in fact, in any phase, new, waxing, crescent, first quarter, gibbous, and full, in any phase, the moon is always half lit by the sun, as well as Earth. Both Earth and moon don't have proper light, so the light comes from the sun, and which means when we see the moon in the sky, we are seeing part of that hemisphere that is being lit by the sun. In the new phase, we don't see any of that bright hemisphere because we're standing on Earth. That bright hemisphere is facing away from Earth. But in the first quarter, the bright hemisphere is facing half of it. In fact, a quarter of it is towards Earth, so we could see it. And then in the full moon, the entire bright hemisphere is facing Earth, and that's why we look at the moon and we see it completely and entirely full. Okay. Now the lunar simulator is a nice simulator for better understand this moon phase. And here's the moon in the new phase. We don't see anything. Now, if I bring the moon to the first quarter, now we see a quarter of it. And in the northern hemisphere, the bright part of the moon is to the right. And the right, as you see the moon, is to the west. Which means the sun is lighting up the moon from the west, and then you can see quite well in this simulation right here. Look at this. So here's us. This is the sun, and this is the moon. The moon is rising for this dude over here. See this dude over here? Let me bring the time. That's the time. Sun is over there, noon, sunset, midnight, and sunrise. So noon can be seen in this box with the sun higher in the sky. But the full moon is, the quarter moon is quarter moon. Now, if allow Earth rotates to sunset, the phase doesn't change. It's still first quarter. But now, the sun is setting. And the moon is high up in the sky. Look at that. The moon is high up in the sky. Now, 6 hours later, midnight, the sun is in the lowest part. Of course, we don't see it. The moon is still first quarter. The moon is setting now. 6 hours later, we see the sun rising. The sun is rising, and the moon is still first quarter. So the main point is the phases are caused by this configuration of sun, moon, and earth, and does not depend on where you are on earth. So it could be anywhere on earth. The phase is fixed. The phase is just one because it depends on the sun, moon's position, and earth in the sky. Now, let's define the phases: waxing and waning, and crescent and gibbous. So crescent phases are this phase and that phase. Any phase in which the moon, and now I'm playing God here and playing with the solar system. I hope I'm not making anybody crazy here. But the crescent phase are the phases in which the moon happens to be always between Earth and the sun. And you see always as a little crescent. It never goes completely full or gibbous. It's a crescent. Now, what's the difference between a waxing crescent and a waning crescent I seen from Northern Hemisphere? So a waxing crescent is one that you can touch the bright part of the moon. You can touch the bright part of the moon with your right hand, as if you could just snuggle and put it right there and take a picture, right? So that is the waxing, right hand. Waning phase, left hand. So which means the sun in the sky, as we see in the sky, the sun in the sky, the waning phase moon, you have the sun in the left-hand side. The moon, the sun in the sky happen to be chasing the moon as both the sun and the moon cross the sky. Now, gibbous phase could be waning gibbous or waxing gibbous. More than 50% illumination, that's what we see it. The full moon is technically 100% illumination. So half of the lit hemisphere is completely turned towards Earth, and we call that 100% illumination. But gibbous is between 50% and 100%. It could be waxing gibbous if you can hold the bright part of the moon with your right hand, and is waning if you can hold with the left hand. So once you have learned or have defined the phases by its crescent or gibbous, waxing or waning, to determine at what time these moons are supposed to rise or set is very tricky. And let me show you a trick that you can do to figure this out. So this is what you do. So let me get my PDF here. So the first thing you do, oh, but I don't have an annotate. How can I annotate? Send, organize. How do I annotate here? Can I do annotation? I can't do annotation. Oh, I think I can do annotation with. Just a second. With Zoom. Just a second. Record. Okay. So sun ray, Earth, and you place. Give me a moon, Rick. A moon phase.
A what?
A moon phase. Give me a moon phase.
Oh, waxing gibbous.
Waxing gibbous. So if the sun is here, Earth is here, we have to know this is noon.
So I don't know if you want to show something, but you just have a blank screen.
Oh, you can't see anything? You can't see anything?
No, we don't see anything, Celso.
And am I taking?
You want a white screen, you got it.
I have a white screen.
You got a whiteboard.
But you don't see none of this annotation, right? I'm right. I'm making
nothing.
All kind of, nothing. Wow. Okay. Well, then we stop here. I have to figure this out. I have to find what's going on. It's a simple trick. Yeah, I have to figure out how can I annotate it properly, and then I post it later. But it's simple, and you can use a simple trick. You have to know how to place let's say a waxing gibbous in the sky in respect to Earth and the sun. But once you locate the moon that way, and you know how to set the clock on Earth, you can figure out at what time the moon is supposed to rise and set. It's almost straightforward. I will show it. That's on me. Sorry about that. All right.
We just got a whiteboard.
Yeah, I can see the whiteboard, but I can write on it, but you guys can't see it. That's so bad.
The cursor's not even moving either. It's like it froze up. It looks
really?
like you were almost successful where I saw a rectangular box where you could usually type something in, but now it looks like that screen's locked up.
Yeah, now I took the screen away and I'm not sharing. Yeah, it's funny because yeah, if I click share on screen, I can bring a whiteboard.
But you can't draw.
But
we can't see it.
Yeah.
Your cursor is moving now. At least there you go.
There's a band.
Oh, the course is moving? How about this?
Yeah.
Oh, there you go.
Oh, can you see it? Oh, okay.
Yeah, the screen was locked up before.
Okay.
Now you're okay.
Okay, so sun, Earth. Since the sun is here, this is noon. Earth rotates like this. This is 6 p.m. Right? This is midnight. And here is 6 a.m. So this is the basic. Place the sun somewhere. Place the sun somewhere. Place the Earth, and then set your time. Now, walks in gibbous, moon in the new phase is here. First quarter is here. Full moon is here. Walks in gibbous is here. This is your walks in gibbous. So what you do, you draw a line from the moon to the center of Earth, and then you do a little T like that. T. So this part of the intersection is the part that this moon is supposed to rise, and the time is 3 p.m. And this part over here, since Earth rotates that way, is the part we see the moon setting. It is 3 a.m. So, roughly speaking, a waxing gibbous moon rises at 3 p.m., sets at 3 a.m. So you take, let's say, a waning crescent. Then we need to know it's here. Then you draw a line and make the T. This waning crescent rises at 3 a.m. and sets at 3 p.m. It's a simple trick, and then you can master this complicated rise and setting time. Now I have some clicker questions. For chapter 2, if you remind them, I can put it in Canvas. I used in a different class, but let's see how we are doing on it. From where on Earth could you observe all of the stars during the course of a year? In fact, I think this is one of my online questions for homework. So if you are in the North Pole or South Pole, you can see only half of the celestial sphere. The equator is the good place, right?
Mm-hmm.
I see in the Northern Hemisphere, these stars are what? Rising or setting?
Say it again.
So I see in the Northern Hemisphere, these stars are what? Rising or setting? So to see rising star, we have to, if we are facing south, in fact, I have to, this is not correct. I see from Northern Hemisphere and facing south, these stars are rising or setting.
Rising in the east.
They are rising. So the east is in our left-hand side. So if we are facing south, we see these stars pretty much rising.
Setting in the west.
And it's set in the west, correct. Ancient philosophers would consider the sun and the moon planets too. So for them, Mercury, Venus, Mars, Jupiter, Saturn, Sun, and the Moon were planets. Pluto didn't exist for ancient philosophers, neither Uranus and Neptune. So those are the sequence of planets according to ancient observers. We haven't studied this yet. None of that. None of that. We don't need to worry about. Asterism. What is an asterism? So we learn there are 88 constellations in the sky, and nowadays, as far as modern astronomy is concerned, constellations are regions in the sky, not group of stars. So asterisms are group of stars with specific names and symbols, and like winter triangle, summer triangle, Orion's belt, Orion's sword, so on. Cassiopeia, the W, those are asterisms. Now, as seen from Northern Hemisphere, what type of moon this is? Is it a waxing or waning? Now, the way to answer this question, you say, okay, how can I hold this moon with my right hand or left hand? So we can hold this moon with the right hand, right? Right? So if it's a right hand, that is a waxing moon, right? So it's a waxing moon. So the sun is up there, but I could ask the question: is this moon rising or setting? And so the proper answer would be this moon should be rising, and is a waxing gibbous moon, basically.
Full moon.
Oh, okay. Look at this one. This is a first quarter. Is a waxing, right? It's a waxing quarter. This is a crescent, waxing crescent. That's a full. That's not a full moon. See this part over here, at the right hand side? It's kind of a dark. So it's a gibbous, but the sharp edge that I can hold on is the left side, right? So my left hand can hold it. So that is a waning gibbous moon. That is a waning last quarter moon. That is a waxing gibbous. That's the crescent. Oh, and then I'm repeating the moons. That's it. So that's just for fun. All right.
Celso.
Yes.
Can you see Polaris and the Southern Cross from the equator?
Polaris. So if you are in the equator, the Southern Cross, you might be able to see it.
But how about Polaris?
Polaris, I doubt it because of refraction, and chances are you might be in the Amazon forest with a bunch of trees and mosquitoes. It's gonna be very much close to horizon. Yeah.
How about if you're like on a mountaintop?
Yeah. Well, I don't know how refraction would do the trick. Yeah.
Okay.
I don't know. I mean, technically you could. That's one of the questions in the homework: which part of the sky, which part of Earth could you stand so you could see all the stars in the celestial sphere? And then the answer is equator, but it's assuming a perfect situation, really perfect conditions, no atmosphere, no nothing, no mountains,
a flat Earth,
a flat Earth, no light pollution, no nothing.
and no pollution.
No pollution. Yeah. All right. So I'm gonna stop taping now.